So, first of all, good afternoon, everybody. My name is Hatem Selim. I'm a senior structure bridge engineer and a project manager at SDR Engineering Consultants. I would like to thank you, MIDAS, and Hope for giving us the opportunity to be here today with you guys and to share with you some of the fun work that we do here at SDR and about the evaluation, structure evaluation of concrete slab spans, as well as reinforced concrete T-beam bridges. And we do the structure evaluation through a combination of load testing and refined analysis. So first of all, what is load testing? So according to the ASHTO manual, load testing, we basically load a bridge with a predetermined load and then measure the response of the bridge under that controlled load to determine the response of the bridge. Generally, the load testing can be static and can be dynamic. I would say most of the time we end up doing the static test. The dynamic, that's mainly done for other purposes than determining proof testing or diagnostic testing, and this what are the statics meant to be. Why the load testing, or what is the benefit of doing the load testing? Basically, when we load test a bridge, we are trying to capture the actual performance of the structure. In other words, we are trying to determine what are the actual live load distribution between the different elements of the bridge. In addition, when we do the load testing, we are trying to account for the factors that we never can include in our design. And many of these factors are like the support conditions of the bridge, the unintended composite action that could happen in reality. Also, some of the secondary members like the railings, the parapets, the bracings, all these elements can contribute significantly to the strength of the bridge, as we will see today. Also, unintended continuity, the fixation that may develop at the end of a slab span or a T-beam span, despite that we are designing as a simple beam, and in reality, this simple beam action or the knife edge support that we use in our analysis does not really exist. And finally, also to account for the actual material properties that we design as a 4,000 PSI concrete, but the actual concrete strength will definitely be higher than that. So what are the advantages of having a load test? The main advantage, and this is what we commonly do, is when we have a bridge that failed the load rating and it is determined that this bridge has to be load posted. In other words, we are limiting the actual live loads that can go on that bridge, since it has a load rating factor of less than 1. Also, we can use it to determine the actual capacity of an existing structure or an existing bridge to see what is the maximum live load we can pass on the bridge, and also establish a load safe carrying capacity of an existing structure. Here in SDR, we do this structure evaluation process. We have developed our kind of procedures based on our extended experience in this area of bridge engineering, that we do a condition assessment, and then after that we do our prelim load rating analysis to determine what are the deficient members. So is it the main girder, is it the floor beam, the stringers, the slab approach span? What elements are the deficient ones that we are going to go and test in the field? After that, we will start with our prelim finite element analysis. We develop a detailed model, as we will show all this later, and then go in the field to do the load test, then come back and validate our finite element model, and then finally update the load rating analysis based on the findings from the field test. So first step, the condition assessment. As you are all aware, we start by doing hands-on inspection. That's very crucial. You have to go out and do a full inspection of the bridge, either if it's a steel structure or concrete structure. As you all aware, we can do the inspection from above the bridge using snooper trucks. It can be from under the bridge, also using a boat. We can access using man lifts, scissor lifts. Also, sometimes we might need to do non-destructive testing to determine some of the characteristics or the material properties, which includes chloride penetration, and that's for concretes. Also determine corrosion, ultrasonic for steel structures or pins. We can do also the infrared thermography. Now, the second step in our procedures is to come up with a preliminary load rating. And this is mainly we do a conventional load rating analysis, same as what we do for any bridge, using the ASH2 approximate analysis methods, and also using many software packages like the ASH2ware bridge rating. We can do it with a smart bridge, which is a software that we also develop in-house. It can be with MIDAS as well. So you do the preliminary load rating analysis. And that's mainly from this conventional analysis, which we typically do for any bridge. You determine what are the controlling spans, which members are the deficient members that we have to go and test in the field, and determine the rating factors of those members. And most probably when we start this would have been already in place, because this is meant for posted bridges. So for a bridge to be posted already, this prelim analysis should have been done using the approximate methods of analysis. After that, before going to do the actual test, we have to go and we have to start developing our detailed finite element model. At this stage, this model serves several purposes. First of all, is to determine the magnitude of loads that we can put on the bridge. We cannot just go in the field and get a truck that is heavy truck and put it on the bridge and end up damaging the bridge while testing. So that's a very important point. We have to determine what is the magnitude of the loads we can impose on the bridge. Then we have to determine what are the safe limits of deformation and strains. So while we are testing, we have to do on-the-fly verification to make sure that the strains we are measuring make sense or are comparable to what we are expecting. And that mainly comes from the finite element model that we developed before going to the field to determine what are the expected strains, so we can do a live comparison while testing to make sure that the gauges are working properly, we are not overloading the bridge, and make sure that the measurements we are taking in the field make sense. And finally, we develop an instrumentation plan by identifying the deficient members to see where exactly we have to place our gauges. Is it like the end, mid-span, positive moment, negative? I mean, depending on the deficiency of the member that we determine from the load rating and from the prelim finite element, we can come up with the instrumentation plan for our gauges in the field. After that, we go, before going to execute, also when we do the finite element, it has to be sort of detailed analysis. We are trying to capture the actual performance of our bridge or structure as much as we can. So sometimes we might end up doing nonlinear analysis. We have to consider sometimes geometrical nonlinearities. We also use different type of elements. It's not only meant for grillage or beam elements. No, in fact, most of the time we use shell elements and solid elements, shell or plate elements and solid elements as well. In some scenarios, we might even have to consider the soil structure interaction, which is one of the nice features in MIDAS, where you can model your piles or foundation and represent your soil using soil springs. And actually, MIDAS, they have a built-in function for the integral piers and the monopiles or the pile and the column, where they can represent the soil using lateral springs and vertical springs using the PY curves method. And I think the lateral springs are nonlinear springs and the vertical springs are linear springs. So this way you also account for the flexibility inherited in the system when you account for your foundation. You expect that when you are modeling a column with a fixed base versus a column where you are modeling the pile and representing the soil, you will expect that the model with the pile and the soil represented will be more flexible, which means you might encounter more deformation, but your internal forces in terms of moments and shears might be significantly less. Now, after that, we go to the field to load test the bridge. So how we apply a load on the bridge, especially that this should be heavy loads. So most of the time we are using, here I'm just start to use my laser pointer, so this helps. So a lot of times we use dump trucks, they call them dump trucks. So we get them filled with sand or limestone, whatever we can get, and we take those trucks and take them to weigh stations. So we determine the axle loads, and we also determine the distance between the loads. And most of the time, those dump trucks were looking into 31 kip load for each axle, and most of the dump trucks we have used before were looking into 4.5 feet spacing between the rear axles, and we're looking into about 5 and sometimes 8 kip for the front axle. What I would like to highlight that those 31 kip and 31 kip 4.5 feet axles spaced at 4.5, this is very close to the HL93 truck. Actually, the HL93 is 32 and 32, but the rear axles are spaced at 14 feet. However, the design tandem is 25 and 25, and they are spaced at 4 feet. So the load we are trying to put on the bridge is very close to the actual design load of the bridge. In very rare situation, we sometimes might have to use counterweights in addition to the trucks. And this was actually for one of the projects that we did, that we had to load each span with 6 trucks, and those trucks were 390 kip. And in addition to those counterweight plates, so we had to put a significant load on the bridge. But this is a different project that I'm not presenting today, but just to show you the idea that we can use dump trucks or trucks in general and counterweight. Also, when we do the load testing, also we have to be mindful of representing the actual design loads. So we can sometimes do one lane loaded situation, which you run the trucks in one lane, and then also you have to do the 2 lane loaded, same as we design the bridges. So we design for 1 lane loaded and 2 lane loaded. After we do the field test, also now for the load, do we go in the field and apply the load or the maximum load on the span? So taking this as an example, this is a simple span, slab span, and we are interested, typically the slab spans are governed by their flexure strength. So we're looking at the mid-span moment for this simply supported slab. So do we go and apply the maximum load on this span to produce the maximum moment at mid-span? I don't think that's wise. You'd like to apply the load incrementally. But how could you apply the load incrementally? And we do this in a smart way. We start moving the load. So we start moving the truck on the span. So you'll see your mid-span moment, your maximum moment is under the load. Once you start moving the truck in and out and getting closer to mid-span, you are increasing your mid-span moment and you're increasing your moment under the load. Same thing, you start moving the load until you move your load to mid-span, and this is what will get you the maximum mid-span moment. So we are incrementally increasing our load and taking measurement at each step. And while we're taking those measurements, we are comparing those measurements to what we are expecting from our prelam finite element model to make sure that we are not overloading the bridge. So the load has also to be applied incrementally in 1 lane loaded case and 2 lane loaded case. Just to give you an idea, so we go in the field also, and we start instrumenting our concrete spans or slab spans or steel. Sometimes we do the same thing for steel bridges, either swing spans or fixed spans, steel beams. We are typically measuring strains and deformation, which could be for concrete or steel. Just those pictures are giving you of an overview of the instrumentation we apply, and this is a picture showing members of the team, Dr. John Gates, and the members of our team while we're sitting on the field to take the measurements while the truck is moving on the bridge. Definitely this instrumentation will show you the pictures, they look nice, but there are a lot of challenges out in the field. In those pictures, yes, we can be standing on the ground and access the spans to be tested. Some other spans, we have to be sitting in a boat doing that. It could be in a snooper truck, can be in a man lift, and there is a lot of challenges to do the instrumentation, like how to access the bridge, when you can access the bridge. If you're working on a swing span bridge, which means they can open the bridge while you're working, you have to secure all your wires. So there are some challenges that comes with the instrumentation as well. Showing pictures for some of the instrumentation that we did on a project, not only for load testing, but also for monitoring the bridge for a certain number of years during the service life of the bridge. Now, after we take our field measurements, we come back and we start compare the field measurement to the finite element model, and then we start validating our finite element model by comparing the field measurement to the finite element strains. And we do that in terms of comparing stresses and strains, and also compare the deformed shape of the bridge to what we're expecting. And then finally, based on the findings from the finite element, from the comparison between the finite element and the field test, what we see in the field, we come back and update our load rating analysis, and mainly to refine our structure analysis assumptions to account for the current condition, also to account for the boundary condition, which is a very important parameter. Also, we might end up updating our live load distribution factors, which we are using from the ASHTO code. These are the approximate equations, or these are approximate analysis equations that gives you the live load distribution factors. So for a specific bridge, we might have to come up with the live load distribution factors, and also for the measured material properties if we have to measure the material strength in the field. So now I will start talking about the first bridge that I'm presenting today. It's basically a concrete slab span. Just to give you an overview of the bridge, this is a swing span bridge, plate girder bridge. So this bridge is open to be opened, and the entire load posting of the bridge was controlled by the approach slab spans. So this entire beautiful bridge is controlled by those concrete slab spans. Load rating the bridge using the conventional analysis and the conventional load rating techniques, they are having load rating factor below than 1. Accordingly, the bridge has to be posted. This was an important bridge, and it's crossing over a big canal, and now you are actually hurting the area on the other side of the bridge. So we have to go and do the load testing to determine what's the actual strength of that bridge and to see if we have to keep it load posted or not. Just an overview, it has 8 concrete slab spans, and each span was 20 feet long. It has 2 tower spans of 30 feet, and it has 1 vertical lift span that was 150 feet. We were interested actually on the concrete spans, so we had to test all the spans. The 8 spans were identical, so we had to go and load test one of those concrete slab spans. To determine which span to test, that's part of the inspection that we do at the beginning. We determine the condition of the spans to see which one we're going to test, look at the current condition, how you can access the span. There's a lot of parameters that have to be taken into account to determine which span that you are going to test, that to make sure it's representative of the 8 spans. This concrete span was 20 feet long, and the thickness of the slab was 12 inches. And you see the bridge, it has a 24 feet roadway, and it has a 5 feet sidewalk on each side, and the sidewalk was elevated as well. And this was a cast in place reinforced concrete slab. The barriers, also the concrete barriers, were cast in place. They were cast as part of the deck. This was an old bridge, so we're looking into concrete strength of 3 KSI, and the yield strength of the reinforcement was 40 KSI. So we start this by developing our finite element model. Typically for the slab spans, we model them using brick elements or solid elements. Yes, modeling using the solid element is a little bit complicated or more sophisticated than modeling with shell elements or frame elements, but that's the only way you can capture the behavior of the bridge, given the fact that you have the slab, the roadway, then you have, I'm pointing here to the sidewalk, which is elevated here, and they had this kind of diaphragms that were supporting the sidewalks. And then the slab at the end is supported on the pile bend. So you can see the model that we are modeling exact geometry for the bridge using solid element. Even the barriers has to be modeled since it was cast in place barrier. So it is an integral part of the bridge. It's not only the slab, but the barriers, the diaphragms, and everything. So this model using the solid element has to be matching, I wouldn't say exactly, but as close as possible to the actual geometry of the bridge. Now, the other trick in the finite element in general, boundary conditions in finite element is one of the most critical parameters that people can play with, and it can significantly change your results. I'm not talking about even structural evaluation, even in design. Just from a structure analysis point of view, if you have a simple beam, just a simple beam, with a hinge and a roller, and with the uniformly distributed load, your moment on this beam is WL square over 8, a hinge and a roller. Just put this beam on a hinge and try to calculate your moment and see what are your vertical reactions. Just as simple as that. That's a challenge by itself. When you put a hinge and a hinge, you will end up having two horizontal reactions that will contribute to your moment. Just look at the strength of a beam that is simply supported on hinge and roller, and go in your finite element model and just change it from hinge roller to hinge and see what will happen to your beam. So the boundary conditions, I always say, it's like it's a lethal weapon. If you don't know how to use it, you can get results that makes you happy, very small moments and shears, and you have a beautiful structures. If you don't know, you can end up also having moments and shears and internal forces that are not representative of reality. So we have to be very careful about boundary conditions even for new designs. When you look at our slabs here, you will see the slabs in general, the slab spans, they are not supported at a specific section. They are supported over 9-inch, and they have this hunch in the slab spans. So you are actually supporting 9-inch of the slab. So your node or restraint cannot be only representing one node. You have to represent the portion of the slab that is vertically supported, that cannot move down. In other words, once you start restraining multiple loads, it implicitly means that you are preventing rotation of this end portion of the slab. And this is a very critical parameter. Once you start preventing rotation at this end part of the slab, it means you are implicitly creating negative moment at this end. And we will see how this will impact the results. Just if you want to try, do something similar and have only the slab supported at one, or prevent the vertical displacement at one node only, versus having this restrained at multiple nodes, and look at the results. So we have to be very careful about the boundary conditions. Also, one of the things, sometimes they have steel bars, which they are called dowel bars, that are coming out of the pile bent or the bent cap, that are embedded into the steel, like similar to what we do in approach slabs. That also will contribute to preventing the rotation if you have the bar or if you don't have the bar. So the boundary condition is sort of critical to be taken care of. But most importantly, you have to make sure that you are preventing the movement along the area of the slab vertically in that direction, since there was no bearing. So this slab was sitting concrete and concrete. So this point cannot move upward or downward because of the bent cap. Just to show you the instrumentation plan. So for this specific bridge, we were instrumenting to measure the strain gauges, or to measure the strains along the entire width of the slab at different locations. So we had, if this is the span length is in the longitudinal direction, which is the 20 feet, and the width of the slab was 30 feet. So we had the gauges at 1/4 of the span, mid span, which is 10 feet, and then 3/4, which is 15 feet. And we also had to measure the strain transversely, and we will show you why we are measuring the strain in the transverse direction and not only along the center line of the slab. And those pictures are showing where we are drilling to put the screws or the anchors into the concrete, so we can measure the strain in the concrete. And then this picture is showing the wires coming from the gauge to the node, and then these nodes are wireless node that transmits the data wirelessly to the base station. For this slab span, as I said, we don't apply the load suddenly on the slab. However, we have to apply the load incrementally, and we do that by moving the load on the bridge. So on this rear, the 31 cap is sitting at 4 feet from the edge. The moment at mid-span will be less. Then you start moving forward. You are increasing the moment at mid-span until you have the load at mid-span. So you have 4 different positions, which means you are increasing your mid-span moment, step 1, step 2, step 3, step 4. So basically what we are plotting here is the strain measured at mid-span at the 4 different positions, which correspond to different moment at mid-span. And those are the lines representing what we measured at the end, at the different width of the slab. The most important message that we'd like to convey here, that increasing the load on the slab and the strain we are measuring, there is a linear relationship between the strain and the load, which means that the slab is still behaving in the linear zone of the concrete, and it means that the concrete is still uncracked. Just to emphasize that, by the way, this loads we are measuring or showing here, this is for two lane loaded. So basically you are symmetrically loading the slab with having two trucks side by side moving forward. So the entire width of the slab is fully loaded by the two trucks. And the moment we are calculating here is basically when we have for position 4, which is position 4 is this position when you have the load at midspan, which is your maximum moment. You are calculating the maximum live load moment on the span, and the corresponding strain we measured in the field was 36 microstrain. And the total dead load moment of the slab is 225, so the corresponding strain will be 17. So your total dead and live is 53 microstrain. And your cracking strain based on the modulus of rupture of the ACKNOWLEDGEMENT, your cracking strain is 132. So this means that your total strain under dead and live load is less than the cracking strain, and this confirms why we are seeing linear relationship between the load and the strain. So by hand calculations, or if you are following the ACKNOWLEDGEMENT strip method to calculate the strain for this slab, which simply the strip method assumes the slab is behaving as a one-way slab in the longitudinal direction, or between the two supports as behaving as one-way, simply supported. Now, when you start looking at the results and the finite element, as we were expecting, you will see that at the end of the slab, you see this blue contour here. This is basically negative strain, which means you have tension at the top, compression at the bottom. And this means that if you took this strip is a longitudinal strip along the slab in the span direction, you will see what we assume a simply supported beam with a positive moment. In fact, this strip we're looking at, it develops negative moment, then you will have positive moment in the middle, so it's more close to like a fixed. I wouldn't say it's fully fixed, but there is partial fixation, and this partial fixation comes from the boundary condition, which is representing the actual seating of the slab. And as I said, this is one of the parameters when we design this bridge, we have to assume it is simply supported. That's the easiest way to design the bridge. However, we are in a situation when we need to look into refined analysis and load testing to see if this is it fair enough for this bridge to be posted or not. So we are not underestimating the capacity of the bridge. And based on our extended experience, we have always realized that bridges, they can carry loads much more than what we would estimate based on code equations. And here's one of the explanations, that you will assume this slab is behaving as a simply supported span. In fact, you are developing negative moment at the end, as you can see from the strains from the finite element, which matches with what we measured in the field. So the development of negative end moments, it helps you reduce your positive moment at midspan. So for example, if you assume this is simply supported, your positive moment at midspan, let's say it's 100 kip feet. When you start doing this negative moment, you will have a negative of, let's say, negative 40, and this 100 will drop to positive 60. So when you do your load rating now, you are not using the 100 kip feet to determine the rating factor. However, you should be using less positive moment, which is 60 given numbers that I'm using. One of the most important things that we have also learned about reinforced concrete slab spans, that once you have the barriers in place, which is an integral part of the slab, going back to the picture before, those barriers, they act actually as inverted beams. And this is a common thing that's sometimes used in structured buildings when you have to have a beam and you cannot drop it under the slab. And if it's an end floor, you can invert your beam. So basically the slab is hanging from your beam, not the slab is sitting on the top of your beam. So going back to this integral barrier, which is a very stiff barrier. So you will expect that this slab is not only supported along the two edges. In fact, those barriers will act as a stiff element that will attract some of the load toward the barrier, and then the barrier will transfer the load to the support. So this simply means that the slab is not only acting as one-way slab, there is a two-way bending action that's happening in the slab. And you can see that when we look at the transverse deformation of the slab. This strip is along the width of the slab. You see you are having, if the slab was acting as one way only in this direction, you would expect that the deformation at the middle of the slab or at the center line is the same as here, same as here, same as here, since it's all the load is running in one way direction. Once you look in the transverse direction, you see the deformation is changing, which means the curvature is also changing in the transverse direction, indicating that some of the load also is going toward the barrier, and then the barrier will transfer to the support. So you also have a two-way bending action. So now two things here, we have the negative end moment and the two-way bending action of the slab. Just to show you what is the impact, the load rating of this slab, before the test, we were looking into 0.75. So it was failing under legal loads. Now, once we just account for some of the negative moment that we could develop due to the end conditions, not even the two-way bending action, you see your load rating factors has increased by almost 40%. So just looking at the behavior of the structures, your load rating can significantly be increased. So it was unfair for that bridge to be load posted based on the capacity of this slab span. Now let me move to the other bridge. I hope I'll remain on time. So the other bridge we are looking at, and I'll make it quick so we leave some time for questions and answers, is a T-beam reinforced concrete T-beam bridges. In general, reinforced concrete structures, they have a lot of redundancy inherited in them. They are not the same as steel structures, and maybe they are not even the same as precast concrete structures. In reinforced concrete structures, simply when we have a beam and a column, we assume the beam is simply supported and it's resting on a column. And we assume this beam will have a hinge and a roller, and when we solve this beam, we're going to develop moment, positive moment as WL square over 8, as simple as that. However, in reality, the connection between the beam and the column, this is a stiff connection. This is an area. So we cannot assume that this beam is simply supported and it will bend as if it's sitting on a hinge. However, there will be some negative moment that will be developed at the connection. And even the column will experience some of this negative moment. That's why the beam column connection is one of the crucial areas that we have to design for when we are doing concrete structures. So by nature, concrete structures, especially the cast in place reinforced concrete structures, they have a lot of redundancy in the system. There is a lot of strength in that systems that we don't account for in our original design. Maybe it's not the same as steel structures, but still, even steel structures and precast concrete structure, there is a lot of parameters that also contribute to enhance their strength without being accounted for in the design. So this was a T-beam bridges. It was a bridge that has a reinforced concrete T-beam and a deck slab. To show the cross-section of the bridge, we had 5 beams across the width of the bridge. It has a 24 feet roadway, so it's a typical 2-lane bridge with barriers as well, and a concrete deck that was 7.5 inch. It was also another old bridge that has a concrete strength of 2.5 KSI, and the yield strength of the steel bars was 33 KSI. Again, we have to model the bridge in finite element, and again, we did that with solid elements or brick elements. And we even in our model, since the barriers were also cast in place and they are an integral part of the bridge, so we have to model them as well. We even include the cross of the end diaphragms of the beams, the sidewalks, and everything. So the model is built to match as close as possible the actual structure. Again, same thing. If you look, those beams, they are sitting on the pile bent or the bent cap, but again, they are not resting at one node. So I zoomed in to show you what's the boundary condition. You see, we had 9 inch of the beam was sitting on the top of the bent cap. There was, and that's why we are preventing the displacement of the nodes along the 9 inch of the boundary, along the 9 inch of the beam. Instrumentation for this T-beams, we actually instrumented all the beams along the span. So we had it at the end, quarter span, mid span, 3/4 of span, and the other end, and we instrumented the 5 beams. Just to show you some pictures of the instrumentations we applied on the beams in the field. And then we start comparing the finite elements also to the measurements. So for the 2-lane loaded, actually, in this case, because this beams, they had the span, let me go back, I think the span was 40 feet. So with 40 feet, when you do the maximum position, you can get 2 trucks back to back, which as you see here, we have 2 trucks. So we're doing 2-lane loaded. That's the loading case that was producing maximum moments on the beam. So we have 2-lane loaded with 2 trucks back to back, which is explained here. We'll have the 2 trucks back to back. So these are the 2 axles of 1 truck. These are the 2 rear axles of the other truck, and we could have 7 feet in between. So this is what will produce the maximum mid-span moment based on the truck configuration that we have. So if we compare the measured strain versus the finite element, also we looked into the boundary condition, if we can do it at the simply supported or the partial fixation. You see, as we are expecting that with the partial fixation, we are getting closer to the measured or the field measures, indicating that the end conditions or the boundary conditions are developing some negative moment, introducing partial fixation of the beam. So it was unfair. It is always unfair for that case, for the beam in the finite element to be modeled as simply supported. And you can see by comparing the finite element to the measured strain in the field. Just to show you the strain contour, you can see that this is how the bridge is bending under the 2-lane loaded, 2 trucks back to back. So we're actually putting 4 trucks on the bridge. I don't know if you have the picture of the trucks on the bridge. No, not here, but we had 4 trucks sitting on the top of the bridge under the 2-lane loaded and 2 trucks back to back. You can still see that, as we always expect, that the bridge will mainly bend in one direction. However, if we look at the strains as well and the deformity shape, you'll see this, the bridges are always have the dishing action. So they're more of 2-way bending action. Again, it depends if the load is symmetric or non-symmetric, if you have the barriers and what are the structure type, but always what we assume as 1-way bending action. Sometimes it is aggressive for bridges, but it depends on the structure type. Again, based on just what we could develop as some negative moments at the end of the beams, you can see that your load rating was 0.85. Now you can go to up to 1.23 easily, just with accounting for some of the negative moment that you can develop at the end of the beam. In the same sense, so it is unfair for that bridge to be load posted, given that it has a lot of strength and redundancy in the system that can take loads much more than what we estimate based on design codes. Now, before I conclude my presentation, I have to be very grateful, and I have to acknowledge the contribution of the SDR team on these 2 projects, specifically the slab span and the T-beam reinforced concrete bridge. The credit has to go to those people. So I would like to thank Dr. John and Dr. Sarah and Osama, Patrick, Gates, Maggie, Sarah, Greg, Reza. They are actually the people behind this project. I don't take credit for these 2 projects by any means. It just happened that I'm here with you guys to present their work to you. I did some contribution, definitely, but I think I have to acknowledge their hard working, and I'm really lucky to be working with such smart people and dedicated people, and I want to make sure that the contributions and the credit goes to them, not to me. Finally, I think our philosophy about load testing, actually Westergaard, I believe he's one of the smartest engineers, and he actually developed a lot of things back in the days in the 50s that were still discovered nowadays. And when you go and dig out things, you will see that he developed some of these things maybe in the 50s and even 40s. And I like this saying. It says, a simple device yields perhaps 80% of the truth, whereas the next 10 would be difficult to attain and the last 10 impossible. But I think back in the days, in the 40s and the 50s, I completely agree with that, and I still agree with that. And that is the philosophy we're trying to adopt here at SDR. Yes, with 80% of the truth, a simple device, which is simply the fundamentals of a structure analysis. No doubt I can do design for very good structures if I have very good understanding of the fundamentals of a structure analysis. And I think this is what people did when they designed and constructed those magnificent structures that we are looking at, even before they developed calculators. They did not even have computers. There was not even calculators to do this long multiplication that we are doing now. Still, they have those beautiful structures that are still surviving up to date. But I think the main reason for that the people had a clear and a very clear understanding of the fundamentals of structure analysis. Now, the next 10% that would be difficult to attain back in the days, and this is where we are relying now on the refined analysis and mainly finite element analysis for structural engineers. And the less than impossible, which we cannot get the real behavior of a structure, and that's why we are doing the load testing. So that with the load testing, you can reveal the actual performance as much as we can to account for the parameters that are impossible to be accounted for in the design phase. So that's the way I can see things. And typically you will see that most of the bridges that are really posted or having a problem, they are always in this area, gray area from 80% to 100%. If the bridge is really having a load factor of 0.5 or 0.4, which means it is almost collapsing, nothing will be done. This bridge has to be replaced. If the bridge is above 1 load rating factor, you don't have a problem. It's always the gray area between the 80% and the 100%, and this is where the finite element becomes very handy, and this is where the load testing could be your savior for the bridge. By this, I would like to conclude my presentation, and thank you for your attention, and I'll be happy to answer some of your questions as long as the time allows us to address your questions. Thank you. Hope, I think you can take over now.
Yes,
and,
thank you. Yeah, we actually have, give me a, yeah, can you see my screen now? We actually have 9 questions submitted.
Okay.
And right now the slide shows only 6, but the next slide will show the rest of the 3.
Okay.
Yeah, I will appreciate if you can answer those questions one by one. Thank you.
Sure. So question number 1, it says, for this slab bridge, how is mesh size determined? Did you do mesh size sensitivity study? Okay, that's a good question. Yes, definitely the mesh size plays a role, and we have done this meshing modeling for so many bridges, so we know roughly what is the mesh size. In general, there are some rules that you would like to maintain for your mesh size. For example, when you have a mesh, you don't like to have aspect ratio more than 4. We always prefer, ideally, to keep our mesh or element size aspect ratio to be 1:1. So if you're doing a plate element, you want to do it 6x6, but you can go sometimes to 2. I would say 3. 4 is kind of the agreed on limit, but I personally like to avoid the 3 aspect ratio of 3. Size-wise, I think for this slab span, we were looking into 6-inch element size, if I remember correctly, but that typically will go between 4 and 12 inches. It again depends on the size of the structure, how many spans you are modeling, and how fast your computer. And sometimes, even if you refine more, you are not getting anything more than that. Question number 2, did you usually find enough reinforcement detail in the negative moment region of the bridge to support your finding from the solid model? That's a very good question. The negative moment is sometimes what we're looking at. You have to look at 2 things. Sometimes even the slab will have a cracking moment that is sometimes significant, and sometimes you will find what is the reinforcement negative moment in this region. And to answer your question, when we do the load rating analysis, we limit our negative moment that we can develop based on the capacity of that section. So if we find, let's say, like 4 bars, our model is assuming the negative moment is a negative 100 kip feet, but you calculate the capacity of the slab at this end based on the existing reinforcement to be 40, so we're limiting ourselves to the negative moment capacity of that section. That's a very good question, but definitely we'll look into that. Bearing, the 9-inch beam is divided into 3. Why do you not divide them? Yeah, that's because of the barrier, the meshing. When we start do the mesh, you have to look at the barrier at the top and the diaphragm. So the diaphragm at this area, I think it was 4.5, so you have to mesh at 4.5, and then you have the elements from the barrier. You have to make sure that everything is connected at the nodes. You cannot have free nodes or elements not connected at the node. Otherwise, you run into numerical problems. So sometimes this is based on the geometry. Ideally, you would love to have it, keep it 3 by 3. I agree. Do you need to calibrate your finite for the validation of your field test? And if so, what are usually the parameters you update? I think the calibration for the finite element model, if you know what you are doing from the beginning based on the experience, so if you are modeling the boundary conditions correctly and you are modeling the barriers and everything, and the actual geometry of the structures, you may not need to do a lot of calibration, or maybe you don't even need to do any update to the finite element model. But I'm presenting this to you after we have tried a lot of things and we have accumulated a lot of experience, so I'm just presenting you the end product. But sometimes you can start without modeling the barrier. Then you start seeing things and you think about why I'm not including the barrier, where it's an integral part of the bridge. Now you start introducing modeling the barrier, the diaphragms, and this is basically how refined your model is at the beginning. So if you end up with a very refined model from the beginning, taking everything into account, then you may not need to go back and do anything for your model after that. So I hope this answered your questions. 5, do you have an estimate of how much savings or monetized benefit your additional analysis brings to DOTs? Yeah, that's a very good question, and actually that's the whole essence about the thing. I mean, you are load posting a bridge, so can you imagine when you remove a load posting from a bridge? Sometimes you have a bridge that's crossing to a community. If you are load posting the bridge, you might be killing the entire business in this area. So when you remove the load posting, you are just not only to DOTs but to communities. Because you have to think a lot of those bridges, they are crossing either waterways, they are crossing a lot of like obstacles in general, so you are connecting communities. In addition, if you load post a bridge, and you have to look at the detours as well, especially for the emergency vehicles. For example, the emergency vehicles, it's also the firefighting trucks. So you have to look into this. Now a detour could be several miles for an emergency vehicle. So this is really, sometimes it's the main motive for the whole thing. The detour for the emergency vehicle is several miles, which means that in case of fire, God forbid, the emergency vehicle will take much longer to get to that place. So the savings is also to DOTs, but it's also to communities as well. For the question number 6, for the T-beam bridge, why 2 layers of nodes are restrained at bearing? That's a good question, but it's a very detailed thing. I can discuss it later, but it's mainly because we had the steel plate embedded, and there was a lot of additional reinforcement at this area. So we had to represent this area with the model that has the equivalent material properties. So we had this plate embedded in the concrete, and this is what we were restraining, if I remember correctly. Question number 7. You said that the loads that the bridge can take is much more than what's considered. Are you accounting for the factors of safety included in design as well? Yes, absolutely. In general, as I showed you, I mean, when we design a slab span, we are assume the slab span is just behaving as a simple beam. That's the strip method. So you have a simply supported span, supported on the 2 ends. And you have seen that now you have negative moments, and then you have also two-way bending action. So this moment that you are designing for, which is the WL square over A, does not really exist. However, we design. So in other words, you design for 100 kip feet, whereas the actual moment under this specific load, let's say, is 60 kip feet. So you have those additional 40 kip feet just only coming from your method of analysis. Other than that, all your safety factors like the fee factors, the ultimate load combination factors, everything else is the same. I meant that they can take even more based on your analysis assumption. Question number 8, have you load tested any parabolic RCT beams? If so, how did the results rating using SDR? Yeah, we did. We had one big bridge that I had on the cover sheet, which is the US 11. This is a big project that we did. It's several miles long. It has 700 something spans of reinforced concrete, curved or arched reinforced concrete T-beam, and we did finite element in terms of linear and nonlinear analysis. And even with the nonlinear analysis, the capacity of the bridge for this curved or arched beams or parabolic, as you're saying here, is way more than that. That's a whole big issue, because it's not only flexure. Now you start seeing arching effect and some of the loads going direct to the support. So that's a whole different thing. But yes, we did that. Question number 9, did you do any material testing to verify the assumed properties used in the analysis? We didn't for that specific bridge. We didn't do any testing, but we are using the concrete strength that I showed at 2.5 KSI, which is an absolute minimum based on the records from the DOTD. But in some projects, we do some testing and it comes out to be higher than that. But to be specific, for the slab span, the concrete strength has no contribution whatsoever to the flexure strength in general. It's all about reinforcement. So in other words, we did not assess the strength of the slab span. The strength is the strength based on the amount of reinforcement in the slab. So you will have, this is your M nominal or your nominal capacity of the slab. What we are looking at is the demand side. Now we're assuming when the slab is acting as simply supported, the demand is 100 kip feet. In reality, the demand is 60 because of the two-way bending action and the negative moment. So what we're mainly assessing is the demand side on the beam or the slab, not the strength of the slab or the beam. The strengths are unchanged, and the concrete strength, I don't think it will have any impact on the flexure strength of the beam. But in some cases, if they want to do the material properties, it is possible, but I don't think it will change much. What matters is you want to make sure that the reinforcement that you have in the existing plans is what you have in your element in the field. I think by this, I hope I answered all the questions. I think you can take over if you don't mind.
Yeah, thank you so much. Thank you so much for answering the questions, Dr.